Welcome to the video for problem 3.5 of Engineering 623. This problem reads as follows. A 10 centimeter length of a K-band copper waveguide is filled with a dielectric material with epsilon r equals 2.55 and tangent delta equals 0.0015. If the operating frequency is 15 gigahertz, find the total loss through the guide and the phase delay from the input to the output of the guide. And furthermore, you were given additional instructions that it was not necessary to calculate the total loss through the guide, that all you needed to calculate was the dielectric loss and still calculate the phase delay. So let's see how this problem goes. If you look at page 102, we have that gamma is equal to alpha sub d, this is the alpha for the dielectric loss, plus j beta, where alpha sub d is given by this formula. And by the way, as is noted here, this formula is also in table 3.2 on page 117. That table, I think you will find quite handy. Now, from Appendix I on page 720, we find that for the K-band waveguide, A is equal to 1.07 centimeters and B is equal to 0.43 centimeters. And from the table, this table 3.2 again, the cutoff frequencies are given by Fc sub mn equals c over 2 pi square root of epsilon r times square root of n pi over a squared plus n pi over b squared. Now, in the present case, as we have already said, epsilon r is equal to 2.55. Let's see here. I just wanted to note one last thing. This expression here for the cutoff frequencies as a function of m and n is the same for the TE and TM modes of the waveguide. So anyway, returning to our discussion, epsilon r is equal to 2.55, and so if we substitute that into this expression for the cutoff frequencies, we get, and then go ahead and substitute also for A and B and for C, we get that the cutoff frequencies are equal to 9.393 times 10 to the 9th times the square root of m over 1.07 squared plus n over 0.43 squared, and that is in hertz. So if we calculate the cutoff frequencies for a few of the modes, these are the lowest cutoff frequencies. The very lowest one, the TE10, will be 8.78 gigahertz. We calculate TE and TM11 will be 23.54 gigahertz. TE01 will be 21.84 gigahertz. TE20 will be 17.56 gigahertz. And so remember that in this problem, we are at 15 gigahertz. So only one mode is propagating, and that is the TE10 mode. All the other modes, since their cutoff frequencies are higher than the operating frequency, they will be evanescent modes. So for the rest of this problem, we can work with the assumption that we are talking about the TE10 mode. And that means then that m is equal to 1 and n is equal to 0. and FC is 8.78 gigahertz. And now we're just about ready to go ahead and find alpha D. Recall that the formula for that is k squared tangent delta over 2 beta. And so clearly we need k and beta. Tangent delta is already given in this problem to be 0.0015. Turning once again to table 3.2 on page 117, we have this formula for k, omega times the square root of mu epsilon, and beta is equal to square root of k squared minus n pi over a squared minus n pi over b squared. So obviously we need to find k first, and then we can find beta. K is very simple, and it turns out to be 159.69 pi. And then when we plug that into the expression for beta, along with m equals 1 and n equals 0, we get beta is 129.486 pi. When we plug k and beta and the tangent delta, which we already have, into our formula for alpha sub d, we get that alpha sub d is equal to 0.464 inverse meters, or you could also express this as 0.464 nepers per meter. Now, if we wanted to express alpha sub d, the dielectric loss, let me rephrase it. If we want to express the dielectric loss in terms of dB per meter, then the way we proceed as follows. We take e to the minus alpha d, calculate that, take the log to the base 10 of that, and then multiply by 20. And we get minus 4.003 in this case. So we can say that alpha D is 4.03 dB per meter. Now that is, note that we're not taking 20 log of this number right here, the 0.464, but we're instead taking 20 log of e raised to that number. So just note that. So here is the value for alpha sub d and dB per meter is 4.03 dB per meter. In this case, the length of the waveguide is just 1/10 of a meter. So the dielectric loss will be 0.403 dB. And finally, for the phase delay, which is frequently denoted by delta phi, that's just beta L, and we've already calculated beta to be 129.486 pi times inverse meters is the units. L, again, is 10 centimeters. And so when we multiply this out, we get delta phi is 12.9486 pi radians, and convert that to degrees, and we have 2,330.75 degrees. So that concludes our discussion of problem 3.5.